So what we're talking about today is exponential models with differential equations. So there's this one special exponential where if you remember the formula, it saves you a lot of time. Could you solve this by separating the variables and not remembering the formula? Yes. So it's not like totally crucial, but it is very helpful. So I have this poster right here. Oh no, I broke it. That's what we're talking about today. So if you have this differential that is proportional, that's what the K means, is proportional to the quantity of the rate of change. So do you see how this is a y and this is a y? Right, that's what tells you, oh, this is my special differential. All right, so that's kind of what we're going to be recognizing today. Before we get into all of that, let's kind of do a little review over exponentials, because you probably haven't seen exponentials in a while. All right, so an exponential function is in the form of a times b to some exponent, and b is your base. That's this guy right here. And your base is always positive. No matter what, always positive. So if you had something like this, y equals negative 2x, the negative is your a value, the 2 is your base. They're separate. The 2 is your b. If it's negative, that's part of your a value. You'll never have a negative as your base number. Does that make sense? Okay. So b is always positive. And you would have an exponential growth if your b is greater than 1. You will have a decay if your b is between 0 and 1, because once again, can't be negative. So you'll be between 0 and 1, which means you'll have some sort of fraction, 1/2, 1/3, something like that. All right, now kind of like what I told you a couple seconds ago, is we are going to be looking at a specific differential. The differential where the rate of change of your quantity, which is dy dt, is proportional to the quantity, specifically that differential. And if you can recognize this specific differential, then you can automatically go straight to this solution. So we can skip the separation of variables. Now I'm going to prove why this works here by separating the variables down below. But if your differential is proportional to the size of the quantity, your solution will be an exponential function. C is going to be your initial condition. And your initial condition, that's going to be when time is 0. And K is going to be the proportionality constant. So kind of we're going to want to figure out what the initial condition is, what the proportionality constant is if it doesn't give it to us, to write this exponential equation, because that would be the solution. All right, so for your exponential growth decay model, once again, if you have this specific differential, dy dt equals k times y, or w dt equals k times w, these two values right here, those two variables, they have to be the same. All right, so if you have this specific differential, you can automatically jump straight to this solution. Now, what is the base of this exponential function here? E. Is E bigger than 1 or less than 1?
Bigger.
Bigger than 1. So that would mean a growth, right? So since your base is E, E is 2 point something, 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 which is bigger than 1, this exponential would give me a growth. Now, there are instances when a decay can happen. And so that is going to be when your proportionality constant is negative. If your proportionality constant is positive, it's going to just be a regular growth. But think about it. What happens when your exponent is negative? Yeah, it goes to the bottom of your fraction, right? And so if you take a really big number and you put it on the bottom, it becomes a really small number. And so that's why your exponential growth, if your exponent is negative, will turn into an exponential decay. Does that make sense? Okay. All right, now down here, this is going to be my proof of why this works. So if you have dy dt equals ky, and I want to separate the variables and I want to come up with a general solution, my first step is always going to move the dt. And so I have my right side as my dt, my left side as my dy. Now what do I want to move to the other side? The y. So I'm going to divide by y because I need all my y's over here on the left. So I've got 1 over y dy equals k dt. Once you have all your y's over here, all your x's over there, then we can integrate. What is the integral of y? Ln of y. What did you yeah. Ln of y, and then what's the integral of k dt?
K squared over 2.
K is just a number. So think about, like, what if we were doing what's the integral of 2? Yeah, it would just be x, but in this case, not an x, a t. So it'd just be kt. Because k is just pretend like it's a number. 2, 3, 4. Think about what would you, if you integrated 3, normally you say 3x, but in this case we would do t. And then plus c. Okay, so now I'm going to solve for y. So how do you get rid of the ln? You e. So then you get y equals e to the kt plus c. And for whatever reason, they don't normally like having the plus c up in the exponent. Where are they going to put it?
In the front.
In the front. And that's going to give you your solution, y equals ce to the kt. So if you don't remember jumping, you could always separate the variables. You could still solve that equation. But if you can remember this specific differential is this solution, you can kind of skip that step. All right, so if we remember the exponential model, we can skip this integration step. So let's look at some of these examples. All right, now the beginning questions here, this is going to be like the very first lesson where you're taking the words and you're writing a differential. So this is the weight of an animal is increasing at a rate. So right there, a rate is telling me that it's d something, d something. And what's increasing is the weight. So it's going to be w dw. And we're in terms of time because this is a real life situation. So the rate you're increasing is proportional. That means I'm going to have some kind of k value. That's your constant of proportionality to its weight, w. It's proportional to the weight, so kw. All right, so the rate part is your dw/tt, the proportional part is your k, and then the weight part there is your w. And that's kind of how you take the words, you write it as an equation. All right, so on 43, bacteria population is shrinking at a rate proportional to its population size. So we're still talking about a rate, so we're still talking about a d something, d something. I'm going to use p as my variable just because it says population. It doesn't really matter what letter you use. If you wanted to use b for bacteria, it just whatever letter you want. And of course, we are still talking about time because this is a real life situation. So dp dt equals, since it's shrinking, what does that mean? Negative k. Yep, so negative k. It's still directly proportional. So we're not dividing. The shrinking just means negative k. And we're still proportional to the population size, which is p. The only time you'll divide, remember, is the word inversely. So it has to specifically say inversely proportional or proportional to the reciprocal for you to divide. If it just says is proportional, that's multiplying. Alrighty, So down here it says find the particular solution for each differential equation. So like I said, if you came across this on the AP test and you didn't remember your exponential model, you could separate the variables, but there's an easier way, because if you can recognize that this is that special differential, because these guys are the same, you can jump straight to the solution, y equals CE to the KT. And we just need to figure out what C and K are. C is your initial condition when t equals 0, which would be what? Five?
Oh,
Does that make sense? Because it's telling me that my value is 5 when t equals 0. So that's going to be 5. K is your constant of proportionality, which is given right here, which would be 6. Is that okay?
It's a little weird.
All right, let's try another one. So this guy here is my special differential. I know it's special because those guys match and it is proportional because it's being multiplied by some coefficient. All right, so I can jump straight to my solution, y equals CE to the KT. And I have to come up with my C and my K. So C is always going to be your initial condition when t equals 0, which would be 4. And then this guy here is your constant of proportionality, -3. The negative just is going to make this be a decay. So it's shrinking, it's decaying, it's losing value, some kind of negative situation happening there. Whereas the positive on this one would be growing or increasing, or I don't know, one of those words. Okay, let's get into some more complicated ones where they have less numbers, more words. So the rate of change of y is proportional to y. That right there is your indicator that this is my special differential. Because the rate of change, dy dt, is proportional, k times y. Proportional to y. And because this is my special differential, I can jump straight to the solution, y equals CE to the KT. Now I need to figure out my C and my K. So the C is your initial condition. Where would that be? 2, because it tells you right here. Initial condition. So C is going to be 2, so I can rewrite this as y equals 2e to the KT. All right, we good so far? Okay, now on this one, it doesn't give me my constant of proportionality. It doesn't say that it is proportional. It doesn't give me that coefficient. But what it does give me is this second point. And so I'm going to use this second point here to find K. All right, so what am I going to plug in for y? 4. What am I going to plug in for t? 2. And then I just got to solve for k. So what are you going to do first? Divide by 2. So 4 divided by 2 is 2. Then to get rid of an e, you're going to ln. So we're going to ln. That's going to totally get rid of the e. And this side, I'm just going to leave it as ln of 2. And then what would your last step be? Divide by 2. So k is going to be ln of 2 over 2. And you can leave it as ln of 2 over 2, or you could get the decimal. Just make sure if you're getting the decimal, you're not rounding too much too soon. So I would write like a couple decimals so you don't get that rounding error. Because of rounding error, I normally try to leave it like this, but you should be safe if you're like, no, that just confuses me, I need the decimal. As long as you put like 4-ish decimals after, you should be fine. All right, so I'm going to take this guy and I'm going to plug it in right here. So my equation is y equals 2e ln of 2 over 2 times t. And now to answer the final question, it says, what is the value of y when t equals 3? So where are you going to plug in 3? Into the t, and then you just have to solve it. So 2e ln of 2 over 2 times 3, and you can just type all of that in your calculator, and it will give you 5.656.
Could we leave it like this 3 ln of 2 over 2?
Yes, you could leave it like this.
If it's FRQ.
Yeah, if it's FRQ. If it was multiple choice, they'd probably have the decimals. But if it was FRQ, I'd just leave it. Okay, let's look at the next one. More words and a real life scenario. An animal weighs 3 pounds at birth and 4 pounds just 3 months later. The weight of the animal is increasing at a rate proportional to its weight. Set up a differential equation for the scenario. How much will the animal weigh when it is 5 months old? All right, so this right here, the weight of the animal is increasing at a rate proportional to its weight. That is your little sentence there that tells me this is my special differential. So dw dt is going to be k times w. The rate of the weight is proportional to its weight. Which means that I can go straight to my solution, my exponential model, y equals ce to the kt. So it's just skipping the separation of variables step. And like I said before, this is the only special differential. We're not going to have like a bunch of them. This is the only one that we will skip the separation of variables. All of the other questions, you will actually work out the whole process for separation of variables. This is the only one where it's this special exponential model. All right, so I know it's going to be, I'm going to put w instead of y, just because I use w. I know I can figure out C because C is my initial condition. Where in your sentence does it tell you what your initial condition is? Yeah, 3 pounds at birth. So W equals 3e to the kt. And then it's going to give me another point to find k. What's that other point?
3, 4.
Yeah. 3 months later, my animal is weighing 4 pounds. So where am I going to plug 3 in? The t, and where are you going to plug 4 in? Yep. And then you're going to solve this, which once again, it's probably going to be an ugly ln. You can either write the decimal or leave it as an ln. But first step, divide by 3. So you get 4/3 equals e to the 3k. To get rid of the e, we have to ln and then divide by 3. So ln of 4/3 equals 3k. Divide by 3. And so k is going to be ln of 4/3 over 3. All right, so I can take that guy and, well, here I'm going to do that in a different color. I can take my k and plug it back in to get an actual equation. W equals 3e to the ln of 4/3 over 3 times t. And then to answer the question, how much will the animal weigh in 5 months? All you have to do now is plug 5 in. So 3e ln of 4/3 over 3 times 5, which is going to give you 4.845 pounds.
So do we need to circle the differential equation as well?
Yes, probably this guy here. You don't have to circle it as long as you've written it down, because it does say to set up a differential equation. So if it ever tells you, like, state what f prime is, like, make sure you state it. You actually don't have to circle anything on the AP test. Like, as long as you write it down, it's counted. So you don't have to circle your answers or anything like that. I generally box my answers and circle them on the keys just so y'all know like where to go. But on the FRQ, you don't have to circle or anything.
Seems like a pain to check it.
Do what?
Seems like a pain to check if no one circles the answers.
Yeah.
I feel like it's taught though, like throughout all the school that people circle answers.
It makes it easy for the teacher to grade. But the graders will look at all of your work. Because just, I don't know, just if you, like, hopefully you won't do this, but if you were to over to the side go like 5 equals 3, like you're going to lose points because that's not true. Like you can't write anything that's untrue. Does that make sense? That's why your work is very important on the FRQ. You have to make sure that your work is true.
That's why you write down everything.
Mm-hmm. Write down everything, write down all your steps. And then if like, I don't know, we'll talk more about like where you would lose points silly least, like in a bad way. I don't know. We'll talk about it more, but yeah, you don't have to circle. Okay. And that's why you just have to be careful with your equal signs, because if you remember how I said you have to write the limit every time.
Mm-hmm.
I don't remember exactly. And if you wrote this equals x plus 4, because you would, if you factored, right? That's not true. This doesn't equal this. This equals the limit as x approaches 3. You know what I'm saying? So like you just have to be really careful with your equal signs. Now if you just wrote that, like if you just wrote it next to it, then that's fine because there's no equal sign. But if you wrote equals, then you're wrong.
What if you wrote like an arrow?
The arrows are good. Arrows work.
Okay.
Equals are, you gotta be safe with equals. But sometimes you need the equal sign, you know what I mean? So it's just, like, we'll talk more about that and how to be safe with the free responses. Okay. Let's do, I'm gonna not do 48. The numbers are really big, but the process is all the same. Is that okay? Okay. So I do wanna do 49 and 50 though, because they're a little different. 49, an experimental population of fruit flies increases according to the law of exponential growth. So right there is telling me that that's my special exponential growth model. Y equals CE to the KT. There were 100 flies after the second day of the experiment, 300 flies after the fourth day. Approximately how many flies were in the original population? All right, so on this one, the question is asking me for the initial condition. How many flies were in the original population? That is asking me about when t equals 0, what is your y? So I'm looking for C. That's the end goal, is to figure out what C is. Whereas so far, we found C first. So that's why this is a different, is we're gonna kind of go backwards. Now, especially when, if you get stuck and they're like listing a bunch of points, I do think writing a table is helpful. So I'm gonna put time t, and I'm gonna put y for the population, or you could put p, it doesn't matter. And I know that at time 0 is gonna be your initial condition C, and that is the ultimate goal, is to figure out what C is. What other point do I know?
Day 2.
Day 2 is how many flies?
100.
100. And
Day 4.
day 4 is
300.
300. So I'm going to take this first point and I'm going to plug it in. So I'm going to plug in 100 equals C E to 2 times K. And I'm going to take this guy and I'm going to plug that one in as well. 300 equals CE to the 4K, 4 times K. And I've got these 2 equations. They both have a C and a K in them. And so I can't solve them individually, but what I can do is I can kind of treat them like a system. Do you remember when y'all did system of equations? All right, it's kind of like that. So I'm going to solve this green one. I'm going to get C by itself, because that's the easier variable to solve for. So I can write C as 100 over E 2K. E to the 2K.
We'll plug that in for C and that.
Yes. And so then we're going to take that guy, plug it in for C right here. And then you have an equation in terms of one variable that you can solve for. So 100 over E to the 2K times E to the 4K. All right, now right here, your bases are the same, E and E. So what can I do to my exponents?
Plus, divide, yeah.
Subtract. Yeah. So when your bases are the same and you're dividing, you can subtract them. So what is 4K minus 2K? 2K. So I can rewrite this as 100 times E to the 2K. So when I divided those guys, that's how I ended up with just E to the 2K. And now it becomes a little bit easier to solve for. I feel like I could go from here. What would you do next?
Divide by 100.
Divide by 100. So you get 3 equals E to the 2K. Then
Take the ln.
ln. So, I don't know, space. So you get ln of 3 equals 2K. And then divide by 2. So that's K. But I don't want K. What do I want? C. And luckily, I have this other equation right here in green where I solved for C. So I'm going to take my K and I'm going to plug it back in.
Doesn't the calculator section, right?
You don't actually need a calculator.
For this?
Because, all right, so this is going to be ln of 3 over 2. Right?
Yeah.
So what's going to cancel?
The 2's.
The 2's. And then you get 100 over E to the ln of 3. And then what else cancels?
ln and E.
The ln and the E. And so then you get 100 over 3. Flies.
I don't know if the ln and the E would cancel.
Yeah. If it's on the non-calculator section, you
You can probably cancel most.
yeah, it normally will work out. Like if you're starting to do something like really crazy, it's probably not right.
That's good to know.
Yeah. Okay, let's do the last one here. A population y grows according to the equation dy dt equals k times y. So I'm like, ooh, looky there. That's my special differential. So I know that that's going to be y equals c e to the kt. Where k is a constant and t is measured in years. If the population doubles every 7 years, what is the value of k? So on this one, all I want to do is find k. Those are sometimes easier, so just make sure also when you're doing your homework, you're reading what the question asks for, because some ask for k, some ask for the equation, some ask for, like, what is the population at this time when you have to do the whole shebang, you know? So don't go too far, is what I'm saying. All right, so on this one, I need to find k. Now, once again, when you're not giving an initial condition, sometimes it does help to make a table to kind of organize all the points that it gives you. So I know at time 0 is going to be my initial condition C. And then it says it doubles in 7 years. So in time 7, what would y be?
2c.
2c. All right, so I'm going to plug this guy in. So I'm going to plug 7 in. 7 in for the time, and 2c in for the y. And what do you notice is on both sides of your equation? A c. So what's going to happen with the c's? They're going to go away, which is nice because I don't really care about the c because this question is saying to find k. So now I just have to solve for k. How do you get rid of the e? ln. So you get ln of 2 equals 7k. And then you just got to divide by 7. So k would be ln of 2 over 7.
It's not that bad.
Nope. It's just, the only downside is another thing to memorize, but it's kind of helpful.
It is. If you get confused with it, you could just solve it through reference, right?
Yep.
If it really comes down to it,
You can just separate the variables and do it the long way. Yeah. Okay, so on your homework, like I said, just make sure you know what it's asking. On 1 through 3, you are just writing the solution, like y equals, so you're just putting it in the form of c equals kt. What is c, what is k? You can get all those values from that. That's why there's not a lot of space right there. And then on 4 through 9, they're kind of mixed up because I want you to be able to read and figure out what it's asking. So I think number 4 is actually one of the more involved ones because you have to actually figure out your k and your c and all of those good things. You have to write your equation so you can plug in 10 and figure out how many people are infected after 10 days. Whereas number 5 is just what is the value of k. That one is not as involved because all you have to do is find k and then you're done. On number 6, all you have to do is find your equation. So you don't have to plug anything in. Once you find your equation, then you're done. 7, what is the value of k? This one, same thing, write your equation. 9 is a little bit more complicated. You're finding the time that your bacteria doubles. So you're finding T on number 9. And then you've got test prep. And that's it. We'll have a homework quiz tomorrow. Also, we're going to talk about the FRQ. So try the FRQ. It's our first full FRQ. Like this was a FRQ question on a previous test. You can do every single part of it. There's 9 points. We're going to see how many points we can get. So I'm going to start kind of throwing those at y'all so we can start practicing those and talking about them.